Hi everyone. Today we're going to continue our discussion on acids and bases. So last time we talked about something called the ion product of water. We saw that water can actually react with itself, or rather another molecule of water, to produce hydronium ions and hydroxide ions. So we wrote out the equilibrium expression for the reaction of two water molecules, and we talked about how we don't typically include pure liquids or solids in our equilibrium expression because their concentrations don't change that much during a reaction. So instead, what we did was we rearranged our equilibrium expression so that K was multiplied by the concentration of water squared, and that gave us our ion product of water, which is Kw. Now we also knew that the concentrations for both the hydronium ions and the hydroxide ions was 1 times 10 to the negative 7th. So we plugged that in for both hydronium and hydroxide ions, and we got a value of 1 times 10 to the negative 14th. So we're going to use that value and this relationship between hydronium ions and hydroxide ions to determine the relative strengths of acids and bases. All right, so we said that Kw is equal to the concentration of hydronium ions times the concentration of hydroxide ions. But we can also use this relationship for other solutions, so we don't necessarily have to use it for just water. So maybe the concentration of hydronium ions is a little bit greater or a lot greater than the concentration of hydroxide ions, or maybe the concentration of hydroxide ions is greater than the concentration of hydronium ions. So this will determine whether a solution is more acidic or more basic. All right, so an acidic solution is one where the concentration of hydronium ions is greater than the concentration of hydroxide ions. So there's a few different ways we can write this. We could just say the concentration of H3O plus is greater than the concentration of OH minus, so that's acidic. Or remember, for pure water, the concentrations of both hydronium ions and hydroxide ions was 1 times 10 to the negative 7th moles per liter. So another way that we could write that we have an acidic solution is the concentration of hydronium ions is greater than 1 times 10 to the negative 7th moles per liter. And that means that the concentration of hydroxide ions is less than 1 times 10 to the negative 7th. So those concentrations, the 1 times 10 to the negative 7th, that indicates we have a completely neutral solution. It's not acidic, it's not basic. However, if the hydronium ion concentration is greater than that, then we get into the acidic solution territory. All right, now remember, these two values have to equal 1 times 10 to the negative 14th. So if the hydronium ion concentration goes up, then the hydroxide ion concentration has to go down to compensate for that change, and vice versa. So they always have to equal 1 times 10 to the negative 14th. Now, what about a basic solution, which sometimes we call an alkaline solution? So this is a solution where the concentration of hydroxide ions is greater than the concentration of hydronium ions. So we could say OH minus, its concentration is greater than the concentration of hydronium ions in solution. So this would be basic. Or we could write that the concentration of hydroxide ions is greater than 1 times 10 to the negative 7th moles per liter, and the concentration of hydronium ions is less than 1 times 10 to the negative 7th moles per liter. Okay. So now that we know more about acidic solutions and basic solutions and what the concentrations of those ions looks like for both, let's do a calculation. So let's calculate the molar concentration of hydroxide ions in a solution that has a hydronium ion concentration of 1 times 10 to the negative 5th moles per liter. And then we'll classify the solution as acidic or basic. Okay, so remember our ion product of water is equal to the concentration of hydronium ions times the concentration of hydroxide ions. So we were given the hydronium ion concentration, and we also know the ion product of water is 1 times 10 to the negative 14th. So let's just plug in the concentration of the hydronium ions, and then that's multiplied by the concentration of hydroxide ions, which we don't know, so we're going to solve for that. Okay, so let's rearrange. We're going to divide both sides by 1 times 10 to the negative 5th. All right, so the concentration of hydroxide ions is equal to 1 times 10 to the negative 14th over 1 times 10 to the negative 5th. Now remember to put parentheses around your values if you're not getting the same answer that I am. That should help your calculation. All right, so I get a value of 1 times 10 to the negative 9th, and that's going to be in moles per liter. Okay, so now we have to classify the solution as acidic or basic. Now we could do this in two different ways. We could analyze the concentration of hydronium ions, or we could analyze the concentration of hydroxide ions. So let's look at the concentration of hydroxide ions. So is 1 times 10 to the negative 9th greater than or less than 1 times 10 to the negative 7th? So our power of 10 is to the negative 9th. And if we're comparing that to a power of 10 that's to the negative 7th, so let's look at 1 times 10 to the negative 7th. And let's write that out in standard notation. So that would be 0.0000001. And then 1 times 10 to the negative 9th is 0.000000001. I think I did that right. So we can see that 1 times 10 to the negative 9th is a lot smaller than 1 times 10 to the negative 7th. So that means that the hydroxide ion concentration is less than 1 times 10 to the negative 7th. All right, so if it's less than 1 times 10 to the negative 7th, is this an acidic solution or a basic solution? So if the concentration is less than 1 times 10 to the negative 7th, that means we don't have a lot of hydroxide ions in solution, and hydroxide ions are basic. So if we don't have a lot of the basic stuff, that means that the solution is acidic. Now, we could have also looked at the concentration of the hydronium ions. So 1 times 10 to the negative 5th is a lot larger than 1 times 10 to the negative 7th. So that means we have a lot of hydronium ions compared to hydroxide ions. And hydronium ions are acidic. So that means we would have an acidic solution. So either way is fine, whatever works for you. Okay, and here's a solution slide if you need it later. All right, so we could just judge a solution's acidity or basicity on the concentration of ions, or we can use an abbreviated form called the pH. So pH is a little bit easier to use. So down below, I'll draw the scale for pH. So pH has a scale of 0 to 14. So right in the middle is 7. So if a solution has a pH of 7, that means it is neutral. If a solution has a pH in between 7 and 14, then it is basic. And if a solution has a pH between 0 and 7, it is acidic. So water is neutral, we saw. So water would have a pH of 7. And then if we measured the pH of a lemon or a lime, we know that there's citric acid in lemons and limes. So that would be acidic. So its pH would be somewhere between 0 and 7. And then if we measured the pH of, let's say, a cleaning solution, let's say some bleach, that would have a pH between 7 and 14. And we can measure the pH of different solutions using a few different methods. So we can use something called pH paper, or we can use an electrode. So pH paper will change color based on whether the acidic solution or whether the solution is acidic or basic. So it'll turn red in acidic solutions and blue in basic solutions. But electrodes are actually more accurate. So electrodes will read how much of each ion is in solution, essentially, and it will give us a digital readout of what the pH is. So how do we actually figure out the pH of a solution? It's kind of an abstract idea, right? So the pH notation is down below. We calculate pH by taking the negative log of the concentration of hydronium ions. Now here they've just written H+, because H3O+, the hydronium ion, is equivalent to just a hydrogen ion. So you can use those interchangeably. Now, we can also rearrange that pH equation to solve for the concentration of hydrogen ions or hydronium ions. So we can take the inverse log of our pH. So 1 times 10 to the negative pH will give us the concentration of hydronium ions, or that's also equivalent to hydrogen ions. Okay, so let's do a couple of practice problems so we can get used to the idea of pH. So let's calculate the pH of a solution in which the concentration of hydrogen ions, remember that's equal to hydronium ions, is equal to 1 times 10 to the negative 9th moles per liter. Okay, so we're going to use that equation we just saw. So we're just going to plug in the concentration 1 times 10 to the negative 9th. So In your calculator, there's a few different ways you can do this. It kind of depends on your calculator. So most calculators, you can just type in negative log, and then parentheses will pop up. And then you can type in 1 times 10 to the negative ninth using the caret symbol. Or you can use something called the EE function. And usually you have to press shift or second before using that EE function. But you could type in 1e to the negative ninth. And either one should work. Now, older calculators, they tend to be a little trickier. So in older calculators, you might have to type in 1 times 10 to the negative ninth, or e negative 9, and then hit log, and then put a negative sign in front of it. So it kind of depends on the calculator. Also, since we're all at home right now, you could use Google, and just in the search bar, you can put in equals negative log 1e negative 9. And that will also give you the same answer. So there's a lot of different options here. So if you're struggling to use your calculator, again, you could use Google, or if you do need help with your calculator, you can always set up an office hour with me. That's fine too. Okay, so pH. This will give us a value of 9. So just double check on your calculator that you're getting the same answer I am. If you're not, then you might have to look up instructions for how to use your calculator, or again, you can always ask me for help. So based on this pH value, is this solution acidic or basic? So let's go back to our chart. So if we have a pH of 9, that's around here. So this would be a basic solution. All right, so pH is a little bit easier to digest. It's easier to interpret than the concentrations of the hydronium ions and the hydroxide ions. And here's a solution slide. Oh, I'm not sure what that is on the bottom. I think I meant to delete that. That's from older PowerPoint slides. All right, so example 2, let's calculate the hydroxide ion concentration for a solution with a pH equal to 4. All right, so this calculation is going to be a little more complex. There's going to be a couple of steps here. So if we're trying to calculate the hydroxide ion concentration, we probably want to use our ion product equation. All right, so we know that Kw is equal to 1 times 10 to the negative 14th. That doesn't change. But in order to calculate the concentration of the hydroxide ions, we need the concentration of the hydronium ions. But luckily, we can figure that out using our equation from earlier, where 1 times 10 to the negative pH is our concentration of hydronium ions. Okay, so let's calculate that first. So our pH value is 4, so we're going to put 1 times 10 to the negative 4th here. Great. And now we can plug that into our Kw, or ion product expression. So we know that Kw is equal to 1 times 10 to the negative 14th. And then we have our concentration of hydronium ions. and we're multiplying that by OH minus. All right, so OH minus, or its concentration, will be equal to 1 times 10 to the negative 14th over 1 times 10 to the negative 4th. All right, so that should give us a value of 1 times 10 to the negative 10th moles per liter. So that problem had a couple of steps. We had to first figure out the concentration of the hydronium ions, and then figure out the concentration of hydroxide ions. So is this solution acidic or basic? And it might be easier just to look at the pH value. So the pH value is 4, which is in between 0 and 7, and we said that that would be acidic. All right, now that also makes sense looking at our concentration of hydroxide ions. It's really, really small. 10 to the negative 10th is a very small value. So that tells us we don't have a lot of basic stuff in solution, which means that it has to be acidic. And here's the solution slide. So let's do another example. Let's calculate the pH of a solution in which the hydrogen ion or hydronium ion concentration is equal to 3.6 times 10 to the negative 4th moles per liter. All right, so we know that to calculate the pH, we need to take the negative log of the concentration of the hydrogen ions. So we're just going to plug in 3.6 times 10 to the negative 4th. All right. So I get a value of 3.44 for the pH. So if you're not getting the same value, again, just double check with me, or maybe use a different calculator or something. I want to make sure you get the right answers, because if you take a quiz, I don't want you to get the wrong answer for your problems. All right, so that's not too bad, right? We're just plugging in the concentration. And then your textbook also kind of steps through how to calculate pH using your calculator. So they do give you some steps to follow here. And again, this will depend on your calculator. So newer calculators actually kind of go in the opposite direction of these rules, but older calculators tend to follow these rules. Or steps. I guess they're not really rules. All right, let's do one last example problem, and then we will end the video. So in this example, we're asked to calculate the hydrogen ion concentration of a solution in which the pH is equal to 5.92. All right, so we saw earlier that to calculate the concentration of hydrogen ions, we're going to multiply 1 times 10 to the negative pH. So we can just plug in the pH value, which is negative 5.92. Now, when you plug this into your calculator, you're going to get a different number or a different scientific notation. And your calculator might give you 0.0000012. Let's see, 1, 2, 3, 4. Yeah, that's right. And we can convert that to scientific notation. So remember, the coefficient should always be between 1 and 10 or equal to 1. So we want our coefficient to be 1.2. And then we have to move our decimal 1, 2, 3, 4, 5, 6 places. And this is a small number, so our power of 10 will be 10 to the negative 6. And then our unit is moles per liter. Okay, so is this solution acidic or basic? And it might be easier to, again, to look at the pH. So the pH is 5.92, so that's between 0 and 7. So this is acidic. Okay, so we'll end there. In the next video, we're going to discuss properties of acids and bases. So I will see you in the next video.